Hello everyone. This is a video that describes upgrading a Hero 1 robot that was built originally by Heathkit in the early 80s. Actually was designed in the 79 and was on sale by 1982. I built one of these with my brother around 1983 or 84. So the robot's about 30 years old, but it still operates very well. As you can see, it has, it's called a Hero 1, and it has a robot arm. Most of the motors in this robot are stepper motors, except for the main drive motor, which is a standard DC motor. And although this robot works well, it still works, and I'll demonstrate that in this video. I'm proposing upgrading it to newer technology. So that it can be more useful in both training and performance, and also battery endurance. I'm proposing a series of videos that show the different stages of the upgrades, and basically I've redesigned or re-architectured the system to work with a modern day microcontroller, the one used by a lot of schools, and it's called the VEX microcontroller. It's called the VEX Cortex. Although the VEX Cortex is not the latest, they've come out recently with a VEX V5. The VEX Cortex can be found reasonably on eBay, and it's a very powerful microcontroller. It's an ARM-based, very similar to the similar to a Raspberry Pi 3 and an Arduino microcontroller. But it has a front end, FPGA front end that handles all the 5-volt sensors and motors, and it can drive up to 10 motors. 8 of them are servo motors, and then the other 2 are standard DC motors that it can drive. And it can read a wide array of plug and play sensors too. So the VEX system is made by Innovations First, and my proposal is to upgrade this Hero 1 robot from the original Heathkit design, which is based on the Motorola 6808 microcontroller. Although the Heathkit engineers designed and built this Hero 1 to be very functional, and they squeezed out the performance of the 6808 microcontroller as much as they could. It was amazing the amount of functionality that they got. This robot can move around remotely. It can detect walls using its Polaroid sonar sensors. It can detect motion. It can also has a voice synthesizer built into it, and all this is controlled via the Motorola 6808 microcontroller. Here you see the front of the Hero 1 robot. It's a 3-wheel based robot, which makes it very easy to steer. The steering is actually controlled by a stepper motor, so it's very accurate. This robot can do all sorts of geometric trajectories readily, easily, because it only has a single wheel, so you don't have 2 wheels. You don't have to worry about PID control at this point. It's a stepper-driven motor, and makes steering very easy. And the steering motor has the main drive motor on it, so it's front wheel drive. The 2 wheels in the back are just freewheeling. Right now I'm showing you the robot with all the panels, plastic panels off. Normally it's surrounded by plastic panels to protect all the electronics, and it looks very similar to a prototype R2-D2 robot. This is the back side of the Hero 2 robot. You can see the very flexible and very accurate robot arm. The robot arm has a shoulder motor, so it's also stepper driven. So the arm can move up and down, and it has a wrist that can both rotate and pivot. So the wrist can pivot to get a degree of freedom, and it can rotate for another degree of freedom. And the arm also extends or retracts for yet another degree of freedom. So this robot has quite a few degrees of freedom. The head itself also rotates to close to 360 degrees. Actually, 0 to 270, I think, because of the limit switches and mechanical stops. But it has a lot, quite a few degrees of freedom. And again, all these motors are all stepper driven, so they're very accurate. And they're open loop control, so you don't have to worry about PID, and you don't necessarily need encoders, although you could use them if you wanted to make it even more accurate, and you can even use PID with the stepper motors to make it more accurate. But there's no need to at this point. For the hobbyist, it's plenty accurate enough. And for a lot of commercial purposes, it would be pretty accurate because 3D printers are done the same way. You can think of this as a 3D printer on wheels. Another novel feature at the time was the teaching pendant that this robot has. The teaching pendant is that little black handle on the bottom left of the robot. It has some switches and a trigger switch which allow you to control all the motion of the robot. It allows you to control the going forward and backward, steering the robot, turning left, turning right. It also rotates the head 0 to 270 degrees, clockwise or counterclockwise. And then it has a switch that allows you to control the arm motors. The arm can pivot, like I said, the shoulder motor can rotate the entire arm, up to 90 degrees either way, clockwise or counterclockwise. And it can also extend the end part of it, the end effector, and it can also control the wrist. It can pivot it up and down, and it can rotate the wrist clockwise or counterclockwise. And finally, it controls a gripper. This arm here doesn't have the gripper, but my other robot has a gripper on the arm. I'm fixing this one. But this is the original configuration that I'm starting from. The robot that I'm upgrading was a broken robot that didn't work very well at all. So I decided to upgrade that one because it would have been very difficult to find all the boards needed to get it working correctly. I kept as much of it that worked, including the 6808 motherboard and the sensor subsystem. So I can still read the Polaroid sensors, and I can also use the original Votrax on the upgraded one. But this one, I'm going to show you how the original works. This is the one that I built with my brother around 1984, 83 to 84, as a college-type training for robotics. My father purchased it to help my brother and me, learn about electronics and robotics at the time. The first step is I'm going to turn it on, activate it, and then I'm going to home the robot. Homing the robot rotates all the arm and the motors to their home position so that it starts out at an initial known position to keep track of the stepper counts. And that way it's very accurate when it moves along because it knows what the stepper counts are. So converting the stepper counts to degrees or to the steering angle, etc., or the gripper opening or closing, is all very dependent on this homing position. So it's a very critical operation at the beginning when you first start up the robot.
Ready.
You heard that sound, ready. That's the first words that the Hero 1 speaks using the Votrax speech synthesizer, which was quite a novelty in the 80s because it allowed the robot to actually speak phonemes. So you could program it with all these phonemes to say different words. This was used for people that were handicapped or for phone systems. It allowed people that couldn't speak to actually use a keyboard and actually sound out the words that they were typing. So it helped the, it was a very good system, and it still runs. It's amazing that that chip is still operating.
Ready.
The LED display uses red LED matrix, and it can actually spell out a lot of the alphabet words. It has some trouble with certain letters, but you can display various messages on it. So it can be used like a an LED display. Displays numbers, and it allows you to program the 6808 microcontroller in assembly using the hex keypad that you see there. The hex keypad also functions as a menu system to make the robot move around using the Heathkit Hero 1 interpreter, robot interpreter, and it has on the right you can see a prototype board that has another board hooked up to it. That blue board that's hooked up with a green LED light is a serial RS-232 card. So that RS-232 card allows you to connect to different computers. I've been able to connect it to my laptop using Windows, or I've been able to use Linux system. I also hooked it up to a Raspberry Pi 3, and it worked perfectly. And it allows you to communicate it up to 9600 baud. Although sometimes it works slower, like maybe even at 300 baud. Okay, I'm going to type 31 to home it. There it's starting, it's homing. You can hear some of the motor starting to move. What it's going to do is it's going to try to take the steering motor and rotate the steering wheel up to 90 degrees and then bring it back to its forward position. And then it's going to try to move the arm to its home position also. And it's going to rotate the head 0 to 270 degrees and move it back to its homing position. This arm, oh, there it's moving the head now. You can see it turning the head. That was the steering wheel that it was moving. And it's going to move the head back to its home position. And again, that's moving with a stepper motor, so it's very precise. But using the Arduino and the Ramps 1.4 boards, those are used in 3D. So I'm using 3D printer Arduino technology, which is very advanced these days. The 3D printers are incredibly accurate, and they're all stepper driven for the most part. So they use the Arduino as the motherboard on the 3D printer, and then they use something similar to the Ramps board, Ramps 1.4, or they use a similar design. Some manufacturers use different designs, but for the most part, it's all compatible, and the software all runs on the Arduino. All the 3D software applications and the firmware is all written on the Arduino. And theoretically, you can just take a 3D printer motherboard, hook it up to the X, Y, Z axis, and hook those into and also the extruder 1 and extruder 2, and hook those to some of the connections that I have reverse engineered on the Hero 1, and then you can control it with a 3D printer board. And you can probably, get very accurate positioning. I mean, the stepper motors here are not the same as the ones in 3D printers. These are older technology. They're not. They're probably. They don't have quite the resolution of the new ones. But still, with the 3D technology, you can still microstep these. So you'll be able to get very accurate positioning, like to grab a can of soda and hand it to somebody, you should be able to do that. And the only problem with the Arduino system is that modifying the 3D printer firmware, you can get the sources online, but it's very complicated, and you would need to tie into the limit switches on the Hero One too, and you'd have to basically hack the 3D printer software to control the robot, and that's a very difficult operation. That's why I didn't go that route. Other than if I plug in a 3D printer, it'll move the steppers. That works. But I've also done the opposite. I've taken the VEX Cortex and hooked it up to a 3D printer and controlled the 3D printer with the VEX Cortex. So you can go both directions. But I decided on the VEX Cortex because it's a very popular construction system, similar to Lego, and it's used worldwide for contests worldwide. And upgrading it to that would be a good demonstration to high school and college students of what you can do to re-engineer an older technology, such as this Hero One, and bring it up to date, re-architecture it, redesign it. And that's sort of what I've done, and that's what these videos will show you how to do. And if you happen to have a broken Hero One robot, you'll be able to fix it pretty easily because the VEX Cortex simplifies that tremendously. It's much easier than working with these older boards. These older boards are very, if one of the chips goes, you have trouble finding them because a lot of them are obsolete. You have to look for them on eBay, and some people might have them and they may not work at all. And the other thing is all these boards on it that you can see are 5-volt TTL, so they drain the battery on this Hero One very quickly. The VEX Cortex is far more efficient, and it should allow much longer run times than the original system. Okay, now I'm going to demonstrate how the teaching pendant works, the original teaching pendant. That's again that black handle on the bottom left, and basically it allows me to control the entire robot. So I'll show you how that works. Printers. I'm going to pivot the arm first. Oh, actually, I'm pivoting the wrist. Alright, I'm going to pivot the entire head. Oh, there it's moving the head now. You can see it turning the head. That was the steering wheel that it was moving. And it's going to move the head back to its home position. And again, that's moving with a stepper motor, so it's very precise. But using the Arduino and the Ramps 1.4 boards, okay, here I'm moving it.